Hi everyone, this is Fowzia Akhter. I am a PhD student at Macquarie University, Sydney, Australia. I am presenting one of my works conducted during my PhD, and it is a graphene-based composite for selective detection of ethylene at ambient environment. So why ethylene sensor development is necessary? As you know that ethylene is one of the major volatile organic components that has adverse effect on human health. Breathing a high level of ethylene, even for a short duration of time, can irritate eyes, lungs, throats, nose, and also there are possibilities of passing out. Hence, WHO emphasizes on monitoring the air quality regularly to identify the sources of air pollution that significantly affect human health. Feasible low-cost ethylene gas monitoring in real time allows identification of environmental hazards in an early stage so that the productive remedy can be planned beforehand. Ethylene sensors can be used for medical application. Human exhale ethylene as a consequence of oxidative stress. If high variation of ethylene in breath is detected for a short amount of time, this could mean a difference between life and death for patients in intensive care. High amount of ethylene release is an early biomarker of bacterial infection, schizophrenia patients, and as well as heart patients. Hence, continuous ethylene monitoring of patients that are on artificial respiratory is necessary to provide right medication at the right time. Ethylene sensors can be used for fruit maturity determination. Ethylene is famously known as the active signaling agent in fruit ripening and seed germination. Climatic fruits such as bananas and apples produce various level of ethylene depending on their developmental stage. Hence, monitoring ethylene concentrations for this kind of fruits is necessary to avoid premature exposure of fruits and flowers that are sensitive to ethylene. So all this monitoring is possible if feasible, low cost, low power, smart ethylene gas sensors is readily available in the market. There are various types of ethylene sensors. Among those, the most popular is optical sensors. These are fast, accurate, and have long-term stability. Their readings do not interfere by other substances. However, these are more expensive and consume high power, and regular calibration is also necessary. There are other metal oxide semiconductor sensors which uses chemical reaction between ethylene and their film. These are highly sensitive, simple fabrication technique, low cost, handy, long life, higher signal strength. However, these require higher operating temperature, more than 100 degrees centigrade to achieve an acceptable sensitivity and also cross-sensitive towards other gases. There are graphene-based sensors. The operating principle of the graphene-based sensors are similar to MOS sensors. The graphene-based components are graphene oxide and reduced graphene oxide. It has a very high electron mobility at room temperature compared to other coating materials. It can detect even lowest level of target species due to their high surface to volume ratio with almost all the atoms exposed to the environment. However, the common shortfalls of those sensors are reversibility, poor selectivity because of weak van der Waals on the graphene surface, while gas adsorption. There are graphene and metal oxide composite sensors. The combination of graphene and metal oxide is an ideal candidate for detecting VOCs in an ambient environment, as the composite compensates the drawbacks of each other. When metal oxide and graphene composites are formed, graphene reduces the metal oxide's band gap energy and enhances the composite's electrical and optical properties. It also improves the sensing capabilities such as reversibility and as well as the operating temperature. Realizing the advantages and disadvantages of various ethylene sensors, we have set the objectives of this research, and these are: synthesize reduced graphene oxide, tin oxide nanocomposite, propose a planar interdigital sensor coated with reduced graphene oxide, tin oxide composite to induce selectivity towards ethylene vapor, analyze the performance of the proposed sensor for differently concentrated ethylene vapor, develop calibration standard, realize the response and recovery time as well as the cost sensitivity of the proposed sensor. To fabricate the sensor, initially it is designed using computer software. Later, a mask writer is used to prepare a 5-inch transparent mask. After that, a positive photoresist is layered on the silicon wafer applying the spin coating mechanism. Pre-baking is also performed at a temperature of 150 degrees centigrade to ensure better attacks photoresist on the silicon wafer. The IDA patterns are transferred on the photoresist coated wafer by using a constant dose of ultraviolet. The silicon wafer is chemically and plasma etched to extract excessive photoresist from the trenches. After that, dissemination technique is applied to spatter on the substrate with 20 nanometer of chromium first and then 500 nanometer of gold for acting as a guard plane. The IDA patterns are 1550. This implies 5 sensing electrode for 1 excitation electrode, and the gap between the electrodes is 50 micrometer. To induce the selective coating of the proposed sensor, the materials used are reduced graphene oxide, DMF, and tin oxide nanoparticle ink. All these are purchased from Sigma-Aldrich and used without further purification. Initially, 5 milligram of reduced graphene oxide and 1.5 ml of DMF are mixed through sonication for 4 hours. At the same time, 250 microliter of tin oxide ink is sonicated for 4 hours for proper dispersion. After that, these two solutions are properly mixed to form the tin oxide and reduced graphene oxide nanocomposite. Before applying this nanocomposite of the on the sensing area of the sensor, it is washed with ethanol and deionized water and dried with nitrogen flow. After that, 3 microliter of mixed solution is drop casted on the electrode of the EMF sensor uniformly for 2 times and dried out at the room temperature. This figure shows the coated surface. The operating principle of the proposed sensor is similar to a parallel plate capacitor. So when a low amplitude alternative voltage is applied to the excitation electrode, and electric field is formed between the excitation and sensing electrode. So when a material under test comes in close contact with the sensing surface, the sensor's impedance changes due to change in electric field. This changing behavior of the electric field is analyzed to determine the characteristics of the material under test. This figure shows the experimental setup for ethylene vapor detection. The experiment is conducted inside a airtight chamber where the temperature and humidity are maintained constant by an external panel. There are 2 mixtures are used to mix the synthetic air with the 10.5 ppm ethylene vapor at a desired amount to prepare various concentration of ethylene gas samples. The concentration of the gas chamber is varied from 0 ppb to 300 ppb, and sensors response in terms of impedance, resistance, reactance, and phase angle and observed. However, in this presentation, only the impedance versus frequency curve is included. So from this figure, we can clearly say that the sensor can detect and differentiate a wide range of ethylene concentrations based on their impedance. So when the ethylene concentration is the highest, the lowest value of sensor impedance is observed. This implies successful adsorption of ethylene molecules on the sensing surface. From the previously curve, we have developed the calibration standard. So this figure shows the calibration equations for high ethylene concentrations and low ethylene concentrations. We have developed 2 calibration equations compared to 1 to achieve the linear equations, as linear equations are easy to interpret compared to logarithmic and exponential equations. Here are the equations that is found from the previous shown graphs. So in these equations, C low ethylene and C high ethylene refers to the calculated concentrations, and Z low ethylene and Z high ethylene represents the values of the impedance corresponding to those concentrations. We have also determined the response and recovery time of the proposed sensors. To determine the response and recovery time, this equation is used. So this figure shows the curve of response and recovery time of the proposed sensors. From this curve, we can clearly say that the response time of the proposed sensor is 3 seconds, while the recovery time is 6 seconds. We have also conducted the cross-sensitivity test of the proposed sensors with other volatile organic components such as acetone, ethanol, acetic acid, and formaldehyde. From this figure, we can clearly say that the response of the sensor towards ethylene is highest compared to other volatile organic components. So from this, we can clearly say that the sensor is highly sensitive towards ethylene. To conclude, we can say that we have successfully presented a ethylene sensor that is highly selective and responsive to a wide range of ethylene concentrations from 0 ppb to 10 ppb, the 0 ppb to 300 ppb. The response and recovery time of the ethylene sensor is 3 seconds and 6 seconds respectively, which is the fastest among all the graphene-based VOC sensors. So all the experimental outcomes showcase that the proposed sensor is potential candidate for real-life environmental monitoring and biomedical applications. Hence, audionable smart ethylene sensing system will be developed in future to apply the sensor in real-life scenarios. Thank you all for attending my presentation. If you have any question, please feel free.